Hello, welcome back to Fractional Calculus. My name is Mittag Leffler. So today we'll be checking Mittag Leffler functions. This functions founded by Gustav Mittag Leffler from the year 1846 to 1927, a Swedish mathematician. So we have our Mittag function of alpha, comma, beta, of function z is giving us summation k equals to 0 to infinity. Z, the function given, is power k, gamma alpha k plus beta. So if our beta is equals to 1, then we also likely have it as our Mittag alpha comma 1 of z. We can also write, instead of putting 1, we can just write only alpha. So we can also have Mittag of alpha of z equals to summation k equals to 0 to infinity gamma k, z is power k gamma alpha k plus 1. So we have this, and then our alpha comma beta sometimes is greater than 0. This case may be. So that is the general function of Mittag, and that is what we'll be using to check some cases. Okay, so let's start with the first case. Case 1, let's find the Mittag function of 1 comma 1 of function of z. So let's start with 0 comma 1, then we move to 1 comma 1, 1 comma 2, etc. So here our alpha is equals to 0, our beta is equal to 1. So substituting these two functions to the general function, we find out that our Mittag is 0 comma 1 of function of z is equals to summation k equals to 0 to infinity z raised to power k over gamma is 0 times k plus beta, which is 1. So in simplifying this, we have summation k equals to 0 to infinity z raised to power k over gamma 1, and gamma 1 is equal to 0 factorial, and 0 factorial equals to 1. So k equals to 0 to infinity, we have zk. So by the time we find this final sum of series of this, we are going to have, when k equals to 0, we have z raised to power k, z raised to power 0, which is 1. When k is equals to 1, we have z raised to power 1. When k is equals to 2, we have z raised to power 2, z raised to power 3, and dot dot dot. So we find out that this happens to be a sum of finite, which is 1 minus z. Okay, so this is the Mittag function of 0 comma 1 of z. Is that okay? So here our z, a value of 1, that is z is in of open interval 0 comma 1. So greater than minus 1 but less than 1. So that's that. So the major thing that you must get to know the sum, the finite series, the sum of series of your expansion. Very, very helpful. So case 2 is Mittag function of 1 comma 1 function of z. So here our alpha is equals to 1 and our beta also equals to 1. So substitute these two functions, we have our Mittag is 0 comma 1, sorry 1 comma 1 of z. Then we have summation k equals to 0 to infinity z is power k over gamma alpha 1 times k, which is k, plus our 1 factorial. So taking this gamma function back to our factorial, sure you should know that our n factorial is equal to gamma n plus 1. So we are going to have zk over n factorial. Sorry, over k factorial rather. K factorial. So now at k equals to 0, we are going to have z raised to power 0 over 0 factorial, which is give us 1. At k equals to 1, we have z raised to power 1 factorial over 1 factorial. Then k equals to 2, we have z raised to power 2 over 2 factorial plus k raised to power 3. K equals to 3, we have z raised to power 3 over 3 factorial plus z raised to power 4 over 4 factorial, etc. So we will find out that this is equal to exponential expansion, which is exponential raised to power z. So that is the Mittag of 1,1 of function of z. Okay, so case 3, we have our Mittag of 1,1. So let's go to 1,2. So with this 1,2, you will to know how to get 1,3, 1,4, and the rest. So here our alpha equals to 1, our beta is equals to 2. So let me rewrite the Mittag function. We have Mittag alpha comma beta of z is equals to summation k equals to 0 to infinity z is power k 1 gamma alpha k plus beta. So substituting our alpha equals to 1 and then our beta is equals to 2. We have 1,2 of z is equals to summation k is equals to 0 to infinity z is power k over gamma k plus 2. That is beta equals to 2, alpha equals to 1, and 1 times k. We have that. So if we take this back to factorial function, we have z is to power k over n plus 1 factorial. So I'm going to divide both sides. I'm going to multiply the numerator by z and also divide it by z so that the equation will not be altered. So with that now, I can have 1 over z summation k equals to 0 to infinity. According to law of indices, the base are equal, then I add up the power, which is k plus 1 over n plus 1 factorial. So this is k plus 1, k plus 1. So here now I say let k plus 1 is equals to n. So and also at k equals to 0, we substitute it here, then we have our n equals to 1. So we substitute these two equations, then we have a new from series. We have summation n equals to 1 to infinity z is power n over n factorial. So we're trying to find the series of this. We have 1 over z. Then at n equals to 1, because this now the summation will start from 1. At n equals to 1, we have z over 1 factorial. At n equals to 2, we have z is power 2 over 2 factorial. At z equals to 3, we have z is power 3 over 3 factorial plus dot dot dot. Okay, so now I'm going to introduce just one kind of trickish term, so that I'm going to have a series that will be minus 1 plus 1, no, minus 1 plus 1 is equals to 0, then plus the series expansion I have here, z plus z is power 2 over 2 factorial plus z is power 3 over 3 factorial plus dot dot dot. So you'll find out that from this 1 down to the series is a series of exponential z. So I'm going to have 1 over z in the bracket minus 1 plus exponential z, which I can also rewrite it as 1 over z exponential z minus 1. So this is the Mittag function of 1, 2 of function of z. Alright, so let's check another case where we have 1, 3 and see what we are going to have as our solution. That will be case 4. Good. Number 4, the Mittag function of 1, 3. So here our alpha equals to 1 and our beta equals to 3. So following the same procedure, we have Mittag 1, 3 fraction of z is equals to summation k equals to 0 to infinity zk over gamma alpha times k, that will be k plus beta, which is 3. So taking this to factorial function, that k is equals to 0 to infinity z is power k over k plus 2 factorial. So here now I'm going to multiply this with z raised to power 2 and also divide it with z raised to power 2. So taking this outside, 1 over z raised to power 2 outside, I'm going to have summation k equals to 0 to infinity, then z k plus 2 according to law of indices over k plus 2 factorial. So here now I can also say let k plus 2 is equals to n, and at k equals to 0, then my n is equals to 2. So putting these two terms, I'm going to have Mittag 1, 3 of z is equals to 1 over z square summation n equals to 2 to infinity z raised to power n over n factorial. So we also find the series of this. We have 1 over z square into bracket when n is equals to 2, so we have z square over 2 factorial. When z is equals to 3, n equals to 3, we have z raised to power 3 over 3 factorial, z raised to power 4 over 4 factorial plus dot dot dot. So in order to make this also an exponential series, so I have to introduce z and 1 plus z so that it can complete the exponential series. However, I also need to subtract it so that I will not alter the equation. That will be minus 1 minus z. So with this now, I'm able to complete the series. So I'm going to have 1 over z square into bracket minus 1 minus z plus exponential z. Okay, so I can just rewrite this as exponential z minus 1 minus z over z square, and that is the Mittag function of 1, 3 of function of z. So with this now, I can just derive the general terms looking at the 1, 1, 2 that are Mittag function, Mittag of 1, n of a function of z is given as 1 over, because when there's 3 here, we have 2 here. That will be, and that 3 is our n, that will be n minus 1. Then our series functional, sure there will be exponential z, then minus the summation of our k to 0 to n minus 2 of zk over n factorial. So we have that as a general formula where alpha is equals to 1 and our beta is of any number. So with that, we're able to get that series. Alright, so let's move to case 5. So at case 5 now, let's increase the value of alpha to 2 and let's take our beta to 1, and let's see the series of solution we are going to have. So here our alpha equals to 2 and our beta is equals to 1. So let's write our Mittag of alpha comma beta, which is equals to summation k equals to 0 to infinity z is power k over gamma alpha a plus beta. So substituting that, we have Mittag 2 comma 1 of z is equals to summation k equals to 0 to infinity z is power k over gamma 2k, because our alpha is now k, it's now 2 rather, and our beta equals to 1. Alright, so if we take this back to our factorial function, this gamma 2k, we are going to have 0 power k over 2k factorial. So I can actually rewrite this z k to be root z, so that you know the order, and also square it and with that k before. So this is k equals to this, so over 2k factorial, then summation k equals to 0 to infinity. Alright, so let's start. So at k equals to 0, that will be 2 raised to power 0, and then that will be with z raised to power 0, which will be 1, and also that will be 0 here also, and everything here also will be 0 factorial, and that's also equals to 1. So I'm going to have 1, and when k is equals to 1, I'm going to have root 2, so with z over 2 factorial. Then when k is equals to 2, I'm going to have with z raised to power 4, and this one is raised to power 2 over 4 factorial. When k is equals to 3, that's with 3, so with z is power 6 over 6 factorial, etc. So you will realize that this is a series function for coch, and that will be coch root z. Okay, so that is the Mittag function 2,1 of function of z. So take note of that. Alright. Okay, so let me quickly just write the series solution of some particular function that will help you in this. So if we have 1 plus x squared over 2 factorial plus x is power 4 over 4 factorial plus x is power 6 over 6 factorial plus dot dot dot. And then this is equal to the summation of k is equal to 0 to infinity, and then x squared k over 2k factorial, and this is the coch x. If you have it as 1 minus x squared over 2 factorial plus, if the sign is changing now, minus plus dot dot dot, so this will give you cos x. Okay, But once you have x plus x3 over 3 factorial plus x5 over 5 factorial plus dot dot dot. This is a sinh function. Sinh function. But if the sign is changing, x minus 3 factorial plus x5 over 5 factorial, we have minus dot dot dot. So this is the sin series expansion. So take note of those expansion. I believe will actually help you greatly. So with that, now we can find that this will be case 6, the Mittag function of 2, 2 of z squared. And don't forget our Mittag function of alpha, beta is equals to a function of z is equals to summation k equals to 0 to infinity zk over gamma alpha k plus beta. So here now our alpha is equals to 2 and our beta is equals to 2. So substitute these two functions. We have our Mittag 2, 2 our function of z is equals to k equals to 0 to infinity zk. So 0 is z squared over gamma 2k plus 2. So if we take this back to factorial, we have z2k over 2k plus 1 factorial. Then equally we can multiply this by z and also divide it by z. So by the time we write that equation, we have 1 over z outside, k equals to 0 to infinity as z is equal to 2k plus 1 over 2k plus factorial. So by the time we substitute the value of k equals to 0, so we have 1 over z, k equals to 0, so we have z over 1 factorial. K equals to 1, we have z3 over 3 factorial. Z is equals to 2, we have z5. K equals to 2, we have z raised by 5 factorial. Plus dot dot dot. So we find out that this is able to be 1 over z and sinh z. So this is the Mittag for 2, 2 of function of z square. So on your own, you can also check let me call it, try this, where we have Mittag 2, 2 a function of minus z squared. So this, if you follow the previous video, we have 1 over z sin z. So you can actually try that on your own. So I want us to check the recurrence. The recurrence relation the recurrence relation of our Mittag function of alpha, beta of z. So you have it as alpha, beta of z to be z times alpha and Mittag function of alpha, alpha plus beta function of z plus 1 over gamma beta. So let's prove this. Don't forget, our formula is given as alpha comma beta is equals to summation k equals to 0 to infinity zk over gamma alpha k plus beta. Okay, so put k to be equals to n plus 1. So if I put that at k equals to 0, I'm going to have my n to be equals to minus 1. So I substitute that into my Mittag alpha comma beta of z. So you have n equals to minus 1 to infinity zk, sorry, that will be n plus 1 into bracket gamma alpha k n plus 1 plus beta. So here now I can let me first of all simplify this. So simplify that I have summation n equals to minus 1 to infinity zn plus 1 over gamma alpha n plus alpha plus beta. Okay, so let me take one of the series that is at n equals to minus 1. That is at n equals to minus 1, I'm going to have z minus 1 plus 1 because n is equals to minus 1 over gamma alpha times minus 1 plus alpha plus beta plus, so my n now equals to 0 to infinity zn plus 1 over gamma alpha n plus alpha plus beta. So minus 1 plus 1, that will be 0. So I have 0 is equal 0. Then gamma, this minus alpha plus alpha, that will be 0. So I have gamma beta left. Plus summation n equals to 0 to infinity zn plus 1 over gamma alpha n plus alpha plus beta. So if you compare, okay, if you compare this summation to the general formula, let me change my pen. Don't forget we have our Mittag alpha comma beta to be a function of z, and then to be summation z equals to 0 to infinity zk over gamma alpha k plus beta. So now because we have n here, we have this here to be k. So we take this our alpha n for the alpha k to have this our alpha. So then first of all the result is by the other 1 over gamma beta plus, then we have that, and also we can see vividly that our n plus 1, in order for it, for our previous solution, you see that we have to divide, we have to multiply this 1 over k and then multiply it 1 over z and multiply it also here z. So that will give us k plus 1. So that means that we have to take the value of z because multiply, that will be z times, now we have our Mittag function, but here now we have alpha k, which is still okay, but here now this is only beta, but here we have alpha plus beta and the opposite side, so we have alpha plus beta of function of z. So this is the recurrence relation of alpha comma beta of a function of z, and this is the major Mittag function formula that you will see in most of journal. So take note of this and then of the proof. Okay, so we stop here in this video, then we continue this Mittag function in the next video. Thank you for watching. My name is Sunday Oluwafemi.